Okay. See if my sound is working here. Okay, so this is the second part continuation of bio and general science intense review. I have a limited time schedule-wise right now, and I'm hoping to pack all the rest of the content in from a standpoint of not having this video be too long for you guys so that you don't have to put too much time into this, but you get a lot of value out of it. But there may be a part 3. It just depends. I will always record another section until I feel like I've at least said everything that's on my A list of things that I must say, and hopefully some of the stuff that's also secondary that can be helpful. I did say I would leave off, or I said when I left off that I would start up at the question that we just worked on, which was last night for me, but hopefully like just moments ago for you. So the other question that's like that enzyme question, the other question that's kind of like what happens when something breaks, and then, you know, what's the most immediate response when this thing breaks? The other example that's very new for this one is a little bit more practical. I would definitely say as far as that type of question where something breaks and you're trying to decide what the result is, that's a hard question type. The acetylcholine sterase version of that is most certainly, at least to date, the hardest question for that. A slightly easier version is, what if the alveoli stop working? And the point that I want to make with this one, because you've been through Anatomy 4 and you know what you're doing with this type of stuff, is I really want to emphasize at some point there will be 10 more questions like this, probably within the span of the TEAS 6, because they do update quite a bit. And so I want to focus on the thought process. The thought process has to start with a very, very focused thought about exactly what do the alveoli do. And this is a little bit easier with alveoli than it was with a neuromuscular junction, because you know a lot more about the alveoli. That's a bigger part of the test in the first place. We don't want to think about the lungs, and we don't want to think about the respiratory system, and we don't want to think about the cardiovascular system and how that connects to the respiratory system. That's all important. That's all knowledge that you have to understand and answer this. But we want to zone in very specifically to the actual alveoli and what they are supposed to do. If you don't do that effectively, there will be at least 2 or 3 answer choices that seem fair, and then you'll have a really hard time getting the right answer choice. On the contrary, if you do zone in and you accurately, effectively determine what this specific thing is supposed to do, you will only have one answer that works. So what do the alveoli actually do? They do the gas exchange, right? And then you need to think into, especially while we're doing intense review, but then when you're on the test, hopefully you've already kind of had the thought process and it's much faster. But you need to picture that. You need to think about, okay, what does gas exchange look like? What is it? What happens? Without expanding your mind frame any bigger than just the alveoli. So you've been studying how the systems work together. So you know that the cardiovascular system has a pulmonary aspect, and that's the time frame during which the blood is in the lungs and this gas exchange is happening. But the answer choices that have to do with blood flow and the pulmonary circuit and the heart, that's not what the alveoli do. They do gas exchange. So what is gas exchange? Gas exchange happens right after we breathe in oxygen. That oxygen is sitting in the alveoli waiting, and as the blood comes through, that oxygen gets into the blood. So brand new oxygen comes into the blood. As a reminder, that is diffusion. So brand new oxygen that just came in from outside diffuses into the blood. And at the exact same time, CO2, so O2 diffuses in, to the blood. And at the exact same time, CO2 diffuses out. So CO2 is going to enter the alveoli, and O2 is going to enter the blood, which means it's going to leave the alveoli. So here's one of our little zoomed in alveoli. When gas exchange starts, we've got O2 right here, and then here's our blood. In fact, let's do a little blood cell. So this is a blood cell, this is the alveoli. And you want to get right down and picture this at this level so that you can make sure your answer is only factoring in the alveoli not working and nothing else. Again, just like with the other question, if the alveoli actually stop working, a lot of things are going to happen. If they continue not to work, yes, that's ultimately fatal. That will stop the heart. That will stop the lungs. It will stop everything that you find in your answer choices. But again, we don't want to go that big with our context. We just want to think about the alveoli themselves. What are they supposed to do? And how does that suddenly change, rather than the steps that would come after that if we were to continue to have an issue. So here's my little blood cell. And let me get some other color here because it's going to be really hard to see if I don't. Let's do some red. So here's my blood cell. And right now my blood cell has CO2. And right now my alveoli has O2. And so the literal meaning of gas exchange, which is the literal job of the alveoli, is this is going to go over here and it's going to go into the blood. And at the very same time, this is going to go over here and it's going to go into the alveoli. That is actual gas exchange. I hope that when I just went through gas exchange, you got a little bored or tuned out for a second because you're totally already on that page. You should know gas exchange that well. You should have some sort of mental image of gas exchange. There's a lot of processes that I would say the same thing about, but from an anatomy and physiology standpoint, you need to know all the big stuff and the systems and what their big functions are and how they work together. And you also need to be able to go to a really small level like this and say the alveoli are one of many, many, many parts to the respiratory system. What do they actually do? So if this is what the alveoli do, this really gives us an answer to the question, what happens the very second that an alveoli stops working? Again, there's no time context. We don't know how long it's going to be down for. We don't know why it stopped working. We're assuming all of them stopped working because it doesn't say like 2 of the 2 million stopped working. So we're assuming for at least a moment in time, all of the alveoli are suddenly not working. So what stops if the alveoli aren't working? Gas exchange stops. They're not going to give you gas exchange. They could give you gas exchange as an answer, and it could be that simple. Most likely, instead of giving you an answer like gas exchange, what they would give you is a description of gas exchange, and they would kind of try to describe gas exchange in a way that it sounds a little bit like maybe something else that's also in an answer choice, to where a couple of them sound close to each other. I've had this question twice on the last 2 times that I've taken the test, so about a week ago and about a month or so ago. The answer choices were a fair amount different each time that I got it. Both times, the answer, we'll start with what is the right answer. The right answer is essentially oxygen doesn't get absorbed into the blood, or oxygen, the blood doesn't get oxygenated, I believe was what one of them was. So it's going to say something about this O2 molecule that's in the alveoli is not going to get into the blood cell. Now, if the alveoli don't work, this oxygen molecule may not even be able to get into the alveoli, because when you breathe in, the alveoli does have to accept that oxygen molecule from outside as well. So essentially, we're going to focus our answer on oxygen. And we're going to say the oxygen's not going to make it into the blood. We don't care so much about specifying that the oxygen isn't going to stay in the alveoli when it passes through, because that's not the job of the alveoli. The alveoli does gas exchange. So when we think about the alveoli, we need to think first and foremost, most importantly, We need to think about the oxygen molecule that's supposed to enter the blood while this is happening. Secondly, slightly less important, we need to think about the CO2 that's in that blood cell that's then going to leave, and it's going to go into the alveoli so that it can leave the body. They will try to trip you up with CO2, and they will try to trip you up with the cardiovascular system. So you're looking for an answer that very specifically zones into oxygen absorption not happening in the blood. The blood is running through the lungs. It's doing that because it's going to pick up oxygen. And one way or another, that blood is not going to get that oxygen molecule. It's not going to pick it up. So that can be worded a lot of different ways. That's why you need to have a visual image and a true understanding of what that actually means in order to find the right answer. What the answer isn't, what you do not want to try to say, is like the blood doesn't go back to the heart. So if you're thinking about how the respiratory and cardio systems work together, you're thinking about the pulmonary circuit. You're thinking the blood goes off to the lungs, then it comes back oxygenated. The fact that it's moving from the heart to the lungs, back to the heart, to the lungs, back to the heart, that is not actually related to the alveoli. The alveoli are not doing that. So would the blood eventually stop flowing between the two? Yes, because if you're not breathing, if you're not getting oxygen, you're headed toward not being alive in any of your systems. So yes, eventually that could be true. And that's the trick of these questions. That's how they make them hard, is all of them are different steps of a possible equation. But 3 of them are steps we can't prove with the amount of info that we have. And one of them is something we can. If the alveoli stop working for a second, the blood that is going into your lungs at that second will continue to flow into the lungs, back to the heart, into the lungs, back to the heart. It's not going to immediately affect the cardiovascular system pumping the pulmonary circuit. It's going to immediately affect oxygen actually entering the blood. Now with CO2, I think only 1 out of the 2 times that I saw this question, there was an answer that had to do with CO2, and I don't remember what it is, but again, let's not study what specifics are. Let's study why we wouldn't answer the way that CO2 would be answered. CO2 is in the blood. It is in that blood cell. The very same blood cell that's taking that oxygen from the alveoli is also going to give a CO2. The answers that they use are bigger than that. It's like the CO2 levels in the blood will drop, and that's backwards. If you can't get the CO2 out, the CO2 levels are going to rise. But again, that is not nearly as immediate as the oxygen not coming in. So they're going to use something that sounds like it's the exact same moment of time, and it's not. They're not going to say CO2 that's in the blood, that's in the lungs, passing through the lungs, is not going to be able to exit. That is just as true as the oxygen not being able to enter. Those are parallel ideas. They won't put both of those as answers. So if they say something about CO2, you'll notice it's something like CO2 won't be absorbed in the tissues. Well, the tissues is not the alveoli, right? That's the opposite end of that chain. We absorb CO2 in the remote tissues, and then we bring it to the alveoli. So if we're talking about the CO2 concentrations throughout the body, or if we're talking about CO2's ability to enter the bloodstream in your foot, that's not the alveoli. So we've just gone out of context, even though they may be making reasonable statements. They may be making statements in the wrong answers of things that could eventually possibly happen. So watch for things that have to do with cardiac. The alveoli stopping does not immediately stop anything related to the heart pumping. It doesn't stop the blood from going back to the heart after the lungs. That is a cycle. The fact that your blood, after it gets oxygenated, pours back into your heart, that doesn't get triggered by oxygen absorption. That's on a timer. Your heart is going to pump at the same speed no matter what. So if the blood goes over to the lungs, goes over to the alveoli, doesn't pick up oxygen, your heart doesn't know that. You have a heart rate. And just like you can feel your heart rate and your pulse, the exact same heart rate is going through the combination of your lungs and your heart back and forth between those two organs. And it's purely based on time. So you're not going to not go, the blood's not going to not return. The heart's not going to stop pumping eventually, but that's not a good answer to the actual question. It's not going to cause, a drop in blood pressure. That would be another thing they could say about the cardiovascular system that could also eventually become true. So there's a lot of things that could maybe eventually become true that are big, they're dramatic, they involve other systems, they involve your life as a whole. All of that is possible. You know how important the alveoli are. But you always, no matter what question you get like this, like I said, there'll be 50 more of these stupid things in the next year. They'll have to do with all kinds of things. The key to a question like that, it's a scary question. What if this stops working? It's particularly scary when it's got a word like acetylcholine sterase in it. That's really scary because you probably don't know right off the top of your head what that even is. But this question is ultimately saying, if any enzyme suddenly disappears from a place where it normally would be found, what happens? The answer to that is always the same, but you have to get very narrow and specific in your thought frame. You have to get very picky and think just about that location, just about the immediate function of whatever you're talking about that's not working or that's gone. And you have to start there and move out. You're never going to move out because you only need one answer. So the other three answers may or may not be things that could factually happen, but it won't matter because you need to pick the first, most immediate, instant result of the actual problem that is listed in the question. So think about those further. If you're not 100% on those, or even if you are, think about them further. If you got extra time in your study, go into any of your anatomy notes, pick something totally random that you have a lot of info on, something we study in depth, and pick something and have it stop working. And you're welcome to send me in the class questions inbox. You are welcome to send me, hey, I did this thing about what happens if this stops working. And I would be happy to look at it. And it's what I want from you is the thought process. I want you to start thinking on that small, specific, narrowed down scale, because we do a lot of thinking on a much bigger scale. We think a lot about the systems and how they connect to each other. And that's very, very important. You must not just know about cardiovascular and respiratory. You also have to know how they work together and what might happen to cause them to have trouble working together. And you also have to be able to get really teeny tiny, microscopic and specific and just talk about one little bitty aspect of one of the systems. I'm not going to talk much about DNA. We do a lot on DNA in Life Science 2. This is a more detailed page of notes. This is my old note page from the TEAS 5. And I don't keep that in the life science class from TEAS 6, although I may put it back there in the future. There's a lot of stuff in here that you don't need. So here's my recommendation. A lot of you do really well if you have additional context. So a lot of you do better knowing actually more about DNA, even though you don't need the answers to these bigger questions. And so I've included more information because a lot of you that take this intense review class are either trying to score very high and everything you possibly could know would count, or you are advanced in some other way. You are looking to further your understanding or further the information you have access to. For that reason, there is a lot of info in this packet. I also included a lot of info about mutation, which is something I used to talk a lot about, but it's not really relevant on the TEAS 6. So I really haven't been. I did put little red brackets around the things that are important. And you'll notice there's a lot of stuff going by that it does not have a red bracket. So if you want to stick with the current mind frame that we have, that we've set up because that's what the test has, just worry more about the red brackets. And or if you did well with Life Science 2 and that all made sense, just go back there. You can still use your notes and the things I drew in that class, and that's fine as well. The things you need to know about DNA, you need to know that it's a double-stranded structure, and it's double-stranded because of hydrogen bonding. That is the most common question that I get. I think every time I test, or darn close to every time I test, I get the question, why is DNA double? Or I get the question, like, 2 nucleotide bases in DNA are connected, how? So hydrogen bonding is a very important one. You need to know what the 4 bases are. You need to know how they pair, right? Because you need to be able to translate a sequence, which is coming up several pages later, but you remember doing that in class. You must be able to take a code and translate it. It doesn't hurt to be able to say which 2 are the purines and which 2 are the pyrimidines. This note page, just an FYI, is organized differently. So you got to be a little bit careful here. I'm not saying right here, I am not saying adenine pairs with guanine. You know that's not true. A pairs with T, C pairs with G. What they're saying right here is that these 2 are big molecules classified as purines. These 2 are little molecules classified as pyrimidines. We always have 1 purine, 1 pyrimidine in each pair. So when we're talking about this hydrogen bonding, a purine hydrogen bonds to a pyrimidine. To give you a visual understanding, we show that here. So if you tried to pair these together, they wouldn't fit because they're both really big molecules that have 2 parts to them. We put one of the littler ones and one of the bigger ones, and they work together and they fit into this space. So you need to know which 2 are 1 molecule type, which is purine, and which 2 are pyrimidine. And then you need much more importantly than that to know how they pair. And then don't forget that RNA uses the letter U, and it's instead of T. You must be able, second most common, there's 3 very common questions that personally I always get. The hydrogen bonding is always one of them. There are several versions of those. They can ask it a lot of different ways. And then there's like, they love to do a big complicated code and they don't put any space in it. They make it like this so that it looks really intimidating. They put the little 3' on one end. They put the little 5' on the other end. You'll see that detailed here. That's a logistical detail. It's not important to you why we do that. That's just how we associate front to back, back to front. All you need to understand about the fact that they call one side the 3 and they call the other side the 5, why these numbers are on the end of your sequences, is that they would be opposite on the opposite side. So if they ask you to transcribe this, make sure you know what is transcription, what is translation, what is synthesis. Transcription is when the RNA has entered the nucleus and it's going to copy the DNA sequence. So that this would be called transcribing if we're going to put the letters for the other side. When I put the letters for the other side, and let me just make this a little more obvious here. So let's say that this side is 3, this side is 5. It doesn't matter which side is which. So far, as far as anything that they have done yet, they do not try to trick you with that. And that's noteworthy because you don't need to worry about the numbers. I'm just telling you about them so they don't freak you out because you haven't really seen them. The proper way to write a DNA sequence, there will be a 3 on one side and a 5 on the other. When you do the other side, when you mirror the strand like we did in the other class, Life Science 2, the 5 will now be over here and the 3 will now be over here. So when you look into a mirror, everything is on the opposite side in the mirror versus in your real self. So when you're looking in a mirror, or better yet, when you take a picture, like people that take selfies in mirrors, it looks like their phone is in the opposite hand of the phone it's in. Because when you're looking at a mirror, everything is swapped. That's the point of the 3 becoming 5 and 5 becoming 3. One sequence will run front to back. So in order to mirror it and attach with hydrogen bonds to it and have its partnered double strand, in order for that to happen, the numbers have to swap. You need to be able to transcribe, and remember that there are 2 possible ways that you could transcribe. One of them would be for them to ask for the opposite side of the DNA strand. The other would be for them to ask for the RNA. Each time that I test, I get some kind of code that looks like this all smushed together. I would say about half the time they say, what is the matching RNA sequence for this? And the other half the time they ask what the partner strand complement is. The technical term for that is the complement strand, partner complement, the other side of the double structure. Because remember, when DNA is in its normal form, it has 2 strips and they are opposite each other as far as code. So you've got a G on one side and a C on the other, T on one side, A on the other, and so on. So they could ask you, they could provide this half, and they could ask you for this half, and that would be the complement strand or the nucleotide base pair strand, anything that doesn't say RNA, essentially. Or they could ask you for RNA. If they do ask you for RNA, remember, you have to go through the steps. You can't go directly from a strand that they provide to RNA. You cannot make a direct transition there. You will get confused somewhere because of the T's having to be changed to U's. So the first thing I need to do is create the other side of the strand. Like this. Then, if that's what they ask for, complement, other side, other half, complementary strand, whatever, base pair strand, if they ask for that, that's it, that's done, that's your answer. If they ask for RNA, I need to take one more step. And now I need to basically copy the code, except the T's will become U. Everything else stays the way it already is. The reason we cannot do that in one step is if you try to bring this to here, you will end up switching the wrong letter to U, because the A's have to become T's and the T's become A. Then we replace the T's. So if you try to do it directly, you'll end up replacing the A with T rather than the T with you'll end up replacing the A with U rather than the T with U. So in order to see where your T's are so you can take them out of the code, you have to have done this middle step. Make sure you know how to do that. Tricks of the trade. What I have always noticed, anytime they give me a question that has this code, first of all, they don't mess with the numbers. So at least at the current difficulty of the T's, I've always looked 5 years into the future and it may change then. Currently, they don't try to trick you by having the right answer twice, but having the numbers switched. They're not going to do something that specific. I'm just telling you about the numbers so that you're aware that they're going to be there. They also tend to give a lot of identifying information. You do not need to translate the whole entire code, is what I'm saying. They will always have answer choices that are so different that you don't need to worry about the entire code. So they give you this big, long code all smushed together, and there's no spaces, so it's really hard to copy that code down correctly. But usually, if you just get the first 3 letters figured out, carefully, of course, make sure you know whether you're doing complement or RNA. Make sure you've got your first 3 letters right, but that's all you'll need to do. The letters will be obvious enough. For example, in this scenario here, whatever we end up translating in these first 3 letters, there's not going to be a G or a C, right? We've got AAT. So if we're doing complement, that's TTA. If we're doing RNA, we're going to have U's. There is no G or C there. 2 or 3 of your answers will have G's or C's right there. You know that's not the translation because there's not supposed to be guanine or cytosine in that part of the code. So it's that simple. Save yourself the time by making sure you're really taking the time to pay attention to which code they want, but don't do the whole code unless the answers are really close to each other, and I've never seen them do that. They're always so different that as soon as you get the first little quarter of your answer, you're done. This is about the hydrogen bonds. We talked about that. This is about the translating here. But we did that with, I would just recommend, I guess, practicing with no space, maybe even practice with the numbers there if that scares you a little bit or changes the way you look at it any. And then remember that you need to be able to kind of spell out this organization of how it is on the small scale of DNA codes to alleles, codes to codons, which make chromatids, which make chromosomes, which make protein. And then also understanding that on a much bigger, broader, and simpler scale, DNA codes for proteins. The DNA codes for proteins part is very, very important. Every time I test, I get a different version. They're always different. They're never the same. Of something that essentially asks you, what is DNA's role, or what is DNA and RNA's role? And I'm just going to write this like this. And they'll say in something. I've seen them say replication. I've seen them say like mitosis or meiosis. Just vastly different things, honestly. And so these questions kind of scare people because I often hear like, well, you never said anything about what they do, you know, in mitosis, although we actually do talk about that in one section of class. And so what I would say about this type of question is I think a lot of people look at this they're trying to be too specific rather than seeing that it's a big, full-scale process question. All you need to know to answer all the different variations of this question, what is their role in something? It's always the same role. DNA is a code. It's a code for proteins. So DNA is a code. This is the thought process. Don't memorize this because you'll be in just as much trouble if you memorize it as if you memorize the question. DNA is a code. This code, in order to do anything, this code can't do anything unless it's replicated. Who replicates? RNA. Sometimes it's specific like that, and that's what you're looking for, is to say that DNA is the code and RNA is the one that takes action and replicates that code. Sometimes it's way less specific than that, and it's more like, what do they do just in general? So DNA is a code, number one. That code does not do anything because it lives in the nucleus and it is trapped there. And it does not do a single thing until RNA actually comes and picks up that code, and that's the transcription process. Ultimately, DNA and RNA together, although they may not put them together, they may generalize and make it sound different than this. When they come together, DNA plus RNA, and the reason I'm saying DNA plus RNA, even though they may not say it that way, DNA is trapped until RNA comes along. So really, DNA codes for proteins, just like we said here. That's the big, 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 big statement. You must understand that. And sometimes you're just going to answer a very detailed question simply by knowing DNA ultimately is supposed to code for proteins. But in reality, DNA is the code for proteins, but it really has to have RNA to actually do anything with that code. So to actually assist in protein synthesis like it's supposed to, you actually have DNA and RNA, and those assist in protein synthesis. We don't quite exactly say that DNA or RNA or the two of them do protein synthesis, because they don't exactly do them. They code for them. They just give information to who does do it. But there's a lot of ways to word that. So if you're talking about mitosis, what is mitosis? Mitosis is where a cell doubles, replicates its information so that it can make another cell just like it. Your liver cells do this all day, every day. So replication would be involved in that. And ultimately coding for proteins. So what is DNA and RNA's role in mitosis? A lot of things, but all of them are going to sound very much along the lines of our points that we have written here. Its role is to facilitate replication or facilitate synthesis of proteins that aid in the making of a new cell, something along those lines. A lot of times they'll have answers where they describe RNA, but they say DNA, so you know how to get past those. Or they'll have something that makes it sound like, you know, DNA actually creates a protein rather than that it assists or it codes or something like that. All of these questions are distributed over a very big space, and it all comes down to the same thing. DNA and RNA are part of a coding process. They work together to bring a code that acts as a template for proteins. Template for protein synthesis is a very common phrase that you'll see for those. Template of protein synthesis. Sometimes they'll make it sound like they do make proteins. And depending what your other choices are, that may be your best choice. And when you generalize and you just take out some language, you may end up sounding like you're saying that. But really, most of the time, we're going to end up with an answer that's like, they assist in protein synthesis. They provide a code. They assist with getting a code to a certain place. They have information for protein synthesis. They participate in the process of protein synthesis. So you know what the little keywords and phrases are. When we talk about DNA and RNA, we talk about codes and blueprints. We talk about replication, which is officially called transcription. We talk about translating to amino acids. We talk about coding for amino acids and also coding for proteins, because those are two steps in the same chain. And that's what you're trying to do. So what you need to have is a proper understanding of where DNA and RNA sit in the spectrum of these bigger projects. And they always sit in the same place. Nothing ever varies with that. Know your basics on RNA. Really, most of the time you're going to use RNA. It's either sitting right there with DNA, like what we just talked about, or you're going to describe something with transcription, or you're going to do a transcription where you give an RNA code. So you don't need to know everything about RNA. A reminder about this chart here. They could, I have not seen this in a while, but I have seen it where they actually give this chart on a test question, which is very intimidating because it looks like a lot of info that you don't know much about. This is an amino acid chart. What you will notice is these are all codons. A codon, as a reminder, is a 3-letter set of DNA sequence. So if I have a DNA code that looks like this, each of these has a 3-letter. When and if you are asked to code amino acids. So remember that after the DNA gets replicated, turned into an RNA code, the RNA goes out into the cytoplasm of the cell. We're seeing that on a very big scale in this chart. And then it does translation. Translation is where a codon or codons give information so that amino acids can be lined up, and ultimately that's how the protein gets made. Every single 3-letter combination that you can possibly make out of the bases is found in this chart here. Nobody, not even probably DNA scientists, have these all memorized. That's not the point. So if you ever see this chart, you're seeing this chart because they don't expect you to have it memorized. There is one mistake here. So if you copied down what I wrote, change the T to a U. Because if we're in translation, we're using an RNA code, not a DNA code. So you'll notice up here, there's no T's in this chart because this is in the translation stage where we've already transcribed and we've turned the T's to U's. Every possible 3-letter combo is in this chart. So all I would have to do if they asked me to identify the amino acids of one of these DNA sequences is I would have to go find this. So this is AAU. That is in this chart somewhere, and it's right here. And so the amino acid that would be coded for is asparagine, I believe. It's really faint on the actual chart. My apologies for that. Asparagine, and then I would go find GCG, and that is right here, and that's alanine. And I could very simply answer a question about an amino acid sequence in a DNA question just by using their chart. So all you have to do is just go find the 3 letters and put the name with it. And that would be a very complex, very difficult question answered very easily. Read through this little thing about DNA mutation. Make sure you know this info. I think most of you've got this down pretty well. Read through DNA mutation to make sure you just develop a basic understanding of it. Currently they don't ask much or really anything, I guess, at the very moment about DNA mutation. It's a good thing to understand. It's very possible that they can ask a very simple question about it. They used to ask about it all the time. And we tend to see when the test evolves, we tend to see it evolve sort of backwards using something that used to be a big thing for the test. And so what you're going to do is probably answer something like, you know, how does mutation happen? Well, it's random. So it's something really simple like that. Remember that you could also very easily be asked about genotypes and phenotypes. A question that I keep getting, I often get the same questions for whatever reason. Most of my students don't, and I do, and I wish that was opposite, is it'll say Gregor Mendel, which is what's coming up on this next page. You remember Mendel because we do the Punnett squares. That was his whole theory. It'll say that he notices a pea plant is tall and has yellow peas or something like that. And then it very simply just asks you, what is he describing? And he's describing a phenotype. He's describing the physical characteristics of the pea plants rather than describing the genotype of, you know, big P, little p, or whatever is in the Punnett square. Make sure you practice on Punnett squares. A lot of these pages look like the pages you already had, but they're not. I went back and I made new Punnett squares for you to do, change the context of the question slightly. Most of you do very well with Mendel's on your own, and there's a very narrow scope of questions that you can actually get for Mendel's. So I'm not going to talk about those at all. Those are from Life Science 2. I would say midway through Life Science 2 probably is where that would be. So you can go back and review that. Make sure that you definitely do have the info that you need on Mendel's. Make sure you know which kinds of questions you can get and that you're prepared to answer them. This is a different practice set, so do practice it. There will be a key, of course, to this class, like always, and I will have these new Punnett squares answered in the key, as well as all the stuff that's about to come up that's got answers as well. This is from Life Science 2. Make sure that you know the structure of an atom, and make sure that you know what an ion is and what an isotope is and how you might get around a question about something like that. I almost always get a question where they name a random atom and they say the atomic number. I tend to get lithium, and I'm going to make up the numbers, so don't hold me to what numbers I'm giving you and the fact that they are or aren't lithium. They'll say something like lithium has an atomic number of 3. And they say this in words. So atomic number like this of 3 and an atomic mass of 7. How many protons does it have? By now, unless it's been a long time since you did my life science lectures, you probably got that down really well. Those are easy to do. So be prepared to just answer how many protons does it have? How many electrons does it have? How many neutrons does it have? They'll give you the info that you need. Protons and electrons, when we are on the periodic table, and in a question this basic, we can totally assume that we are not talking about a lithium that is in a chemical bond with something else participating in a molecule. We're talking about just lithium, the way that it would be on the periodic table in its simplest, most natural form. Protons and electrons, the information is in front of your face for those. It's the atomic number. So if they ask you, if they give you an atomic number and they ask you how many protons or how many electrons something has, it is the atomic number. Done. That's only true if we're not in a chemical reaction, we're not participating in a molecule situation. But if they're just asking you something as simple as how many electrons are in this atom or how many protons, it's usually protons that they ask about. It's just the atomic number. The one that you got to go a little out of your way on is if they ask you for neutrons. Neutrons do not have a number that is visible from a periodic table entry. Neutrons, we have to use two numbers. Again, let's use the same example. So they said lithium has an atomic number, I'm going to abbreviate that, of 3, and it has a mass of 7. And I am certain that those were the numbers that I had last time. I'm not certain that it was lithium, but it was something very close to that if it was not. And if they asked you for protons, you would say 3. And if they asked you for electrons, you would say 3 because that's the atomic number. If they ask you for neutrons, remember that what you have to do is take the mass. The mass is obtained, that number is obtained by adding protons and neutrons together. That gives you the mass number. We always have the number of protons because it's the atomic number. So what you do is you take the mass, in this case 7, you subtract the number of protons because we have a very simple equation here. We add two things together and we get this number. We know what this number is that we get, and we know what one of the two things is that we added together. And so all we have to do is say, well, if you took out that 3, what would be left? 4 neutrons. 3 plus 4 is 7. We get the 3 from here. We got the 7 from there. This would be 4 neutrons. Simpler than what I just said. Remember that you also need to be able to say a proton contributes to what, and a neutron and an electron contribute to what, or don't contribute to what. What I mean by the don't contribute to what is, so there's charge and there's mass, and that's it. Charge would have to do with the imbalance of negative and positive forces, protons and electrons. Mass would have to do with the physical presence, the sort of like the weight of the atom. Protons are the one thing that affects both. Protons give positive charge. Protons contribute to mass. And they're also the atomic number, which makes it easier to remember how important protons are, because basically the element gets named and numbered based on its protons. That's how important protons are. Neutrons only contribute to mass, and that's why we have to do that little mathematical equation to get the quantity of neutrons. We cannot find that in the charge. We can only find that in the weight. And then electrons, we only find in the charge, not the mass. It's common for a question to say which particle or which part of an atom is negligible. They love that word because people hate that word. Negligible in calculating mass. What that meant, don't memorize that. What that meant is which of the three things, proton, neutron, or electron, doesn't have an effect on the atom's mass. We add up protons and neutrons when we're talking about mass, so electrons are not in there. Physically, there's a great reason for that. Protons and neutrons are in the dense and heavy part of the atom that actually has the atom's weight. Electrons are outside on basically magnetic rings that are like floating through space. So if you think about like not having gravity and how you float, that's kind of how electrons sit. And that's the way that I always remember and understand that they don't have mass. They're not actually in the atom exactly. So be prepared for those. Understand just a little bit about ions and isotopes. The term ion comes from ionic bond. And of course, I could be saying that backwards. Ionic bond might come from ion, whatever. They are roots of the same word. When you see ion, it is a charged particle. When we're on the periodic table, we always assume we have the same number of protons as we do electrons, which means we always have no charge, because if you have 5 units of positive and you have 5 units of negative, you're at 0. So you're not charged. Only if something changes about how many protons or how many electrons we have, only if something changes about one of those things would we get a charge. And when we do get a charge, when something does change there and there is an imbalance between proton and electron count, we call that an ion. There are cations and there are anions. And I believe that's somewhere here. So a positively charged ion is called a cation, and a negatively charged ion is called an anion. They don't use that a lot, but it doesn't hurt to have that. And there's something extremely important, especially for something that's coming up that we're going to talk about. That's why you need to know this and understand this. Typically, the TEAS doesn't make you actually form a chemical bond. I've very occasionally seen questions like that, but they later disappear, and they're probably the unscored questions. The HESI, just as a note, definitely you have to be able to actually draw a bond for the HESI. So if you are taking HESI, that is very different. If you are taking HESI, but you're hearing me right now, we either did things a little differently, or you're taking TEAS and then you're taking HESI. And if that's the case, you will do a totally different set of biology classes optimally for HESI, because it is much harder. Protons do not move. This is explained right here, and I cannot say it enough times. Chemistry is a very hard class, and it would be a much easier class if chemistry professors simply explained protons don't ever go anywhere, and the quantity of protons that something has cannot be changed ever by any force in any situation for any reason. So when you look at your atomic number, you can guarantee that is truly the number of protons, truly always the number of protons. If you're not engaged in a bond, you can also say that atomic number is how many electrons. What that means is every atom starts neutral. Every atom starts with the same number of protons as electrons. So here's a few examples. If something is, these are all periodic table. These are before a bond, no bond. If there's 4 protons, there's also 4 electrons. If there's 5 protons, there's 5 electrons. If there's 1 proton, there's 1 electron. What do these all equal out to? 0. This number right here will never change. So if you're trying to understand what's going on with a particular atom, if you're trying to picture it in its bond, you know what the protons are doing as long as you have the atomic number, and you will. So don't ever change this. What gets confusing is when we change 2 different things, because if 2 different things could change, then there would be basically countless ways to wind up with a different charge. And that's what you want to avoid. There's only one way that an atom can become -1 or +2. There's only one way to end up with that charge. The electrons move. Electrons can be shared, which is covalent bonding, and electrons can be given away or taken on, brought over from another atom. An atom that's got just one stupid electron in its valence shell is going to be very happy to give that away to somebody so that it can get rid of that outer shell and have a nice and balanced inner shell. Remember that the goal of an atom is to have 8 electrons in its outer shell. It is not stable unless it does. There's 2 ways to get 8 electrons in your outer shell. One of them would be to get rid of 1 or 2, maybe 3 electrons out here, get rid of those, and then just get rid of that whole shell, and now you're at 8. The other is to, let's say, the opposite. So let's talk about who would actually join up with this guy. So I'm going to do sodium and chlorine because that's a very important bond, first of all, for a nurse, and is a very common one. So here's sodium, here's chlorine. I'm going to be a little inaccurate here with this, just for the sake of time. So don't pay attention to all of my electrons here. And not that you care. You probably do not care how many electrons these things actually have. But don't pay attention to that. All I want you to look at is the very outermost shell, and I'll make it a different color. So this is to make a fast, easy scenario. Chlorine loves sodium, and the reason that it loves sodium is because chlorine has 7 of its 8 electrons in its outer shell. It is almost stable, but it's not. So it has 7 out of 8 electrons. Sodium is quite the opposite. It's got a stupid outer shell that it doesn't want to have because it's only got 1 electron in it. So when we look at how bonds are formed, it's very simple to just kind of say what would be practical. If I'm really OCD and I want to make sure that I have exactly $1,000 in cash, if I have 900, it's going to be easier for me to obtain 100. If I have 1,100, I'm going to try to give away that 100. Obviously, hopefully you wouldn't do that with money. If I am sodium here, Na is sodium, I want to just give this electron away because then I'm stable. I can just get rid of that outer shell that was there just to hold that 1 electron. If I'm chlorine, I just need to get 1 electron. And so when this electron moves over here, we now have 2 stable atoms because now they both have full valence, but we've changed the charge of each of them. Sodium just got rid of an electron. It just lost 1 electron, right? Make sure you agree with that. Make sure you understand exactly why I'm saying that that's the case before we do the mathematics of this. Chlorine just gained 1 electron. Of course, this happens in all different numbers. Sodium lost an electron, chlorine gained 1. If sodium lost an electron, and I'm going to make up sodium and chlorine's atomic numbers instead of looking them up. I should know them, and I don't. So let's say that sodium had 7 protons and 7 electrons to begin with. This is to begin with. So let's say sodium has an atomic number of 7. It doesn't, but let's say that it does. And let's say that chlorine, actually I know what chlorine's is. Chlorine's is 17. Sodium is 11. Write that down, 11. We're going to change to be accurate because I just remembered what the answer to that is. Obviously, I'm not a big fan of chemistry. Okay. 17 and 11. That's the real numbers, I think. Don't hold me to it still. So if they started there, they were both neutral. Neither of them had a charge, and that's good. But they were each unstable in their own way. That's why they wanted to bond. That's why they went and found each other and made this exchange, as they were unstable because of the fact that they didn't have full valence. So if I lose an electron, if I'm sodium, I now have 10 electrons because I gave 1 of my 11 over to chlorine. And then in turn, if I am chlorine, I now have 18 electrons because I gained 1. What is the new charge instead of 0? What is the new charge of each of these? Sodium is now +1. Why? Because there's one more proton. Protons are positive, electrons are negative. If you add 11 plus negative 10, you get a positive 1. If I add 17 and negative 18, my charge would be -1. These are both ions now. This is now an anion. It's negatively charged, and this is now a cation. These are attached to each other because this was an ionic bond that happened here. And they're attached because of the negative and positive pull that it causes when you move electrons around. So this is important for a few different things. You don't need to be able to draw these. Obviously, if your instructor doesn't have these atomic numbers memorized, you certainly don't need those memorized. They will give you a periodic table if they're going to ask you for something like that. They typically stick to things that they can really easily give you, which is great. They tend to stick to things like, you know, hey, the atomic number of this is this. What's its protons? The charge of this is this. How did it happen? So it's usually all verbal, and you don't need a periodic table or a charge or anything. So that's what you need to know about ions. Isotopes vary in mass. So not only can the charge of a particle change, so can its mass. And we're not going to be, when we think about ions, we think of it actually changing in front of our eyes because something bonds with something else and suddenly numerically everything changes. Isotopes are not that way. The way isotopes work is there's a hydrogen over here on my left shoulder and a hydrogen over here on my right shoulder. And by nature, they don't quite weigh the same amount. That's a natural occurrence. You just need to know that that exists and understand how that works. I could have, and hydrogen's a very poor example because of how little it is to begin with. Let's say chlorine. I could have a chlorine on my left shoulder and a chlorine on my right, and the atomic mass of one of them might be 24, and the atomic mass of the other one might be 25. And that's naturally how these are occurring. That's just how they came. Just like humans, no human has the exact same build. And so an isotope, the only reason they would mention an isotope or ask you a question is to essentially ask you to do the neutron math. The same neutron math we did a minute ago where we took the atomic mass and we subtracted the atomic number. What they could do is say something like this. This example is perfect for how it's written. They'll say something like 018, and I want you to know what that is so that you don't freak out when you see that. When they do an element name, so they could also do this with like Na12 or Cl24, they're saying oxygen with a mass of 18, sodium with a mass of 12, chlorine with a mass of 24 is what they're saying. What they would be basically asking you is exactly what's in the example. 018 is an isotope with a mass of 18. You don't really care when you see this question whether that would be the mass that you would see on the periodic table or whether that's one of the variants. You don't really care. You just need the numbers to be given to you so that you can do the math. So they'll give you the weight. Sometimes they'll give it like this. Sometimes they'll describe it and say it's an isotope and here's its mass. But one way or another, they will give you an atom. They will give you a mass. And they will give you its atomic number. The atomic number, of course, is because that's the protons. And just like we did a bit ago, you'll take whatever mass they give you. You don't care how normal that mass is. You don't care if it's outlandish or if it's totally normal for it to weigh that. You just care to take the 25, subtract the 8, and find out what its new mass is. Or what it's not its new mass, but it's neutrons, its new level of neutrons. This question would always be how many neutrons does it have? And as far as from your standpoint, the only difference between an isotope question that asks for how many neurons versus an atomic, periodic table question, there's only one difference, and that's that these will look a little tricky. They'll have like some numbers that maybe look like symbols you don't recognize. So they might just look a little harder than a periodic one, but they're the same thing. And those are not ultimately very common. It's much more common to be asked about electrons and charge and atomic number and how many protons and stuff like that. All right, I have so little time and I so want to get through the biology part of this and then record the general science by itself because it's going to be a very quick segment. So I'm going to try to go really fast for this. Label right here, reactants, products. They've recently started adding a little kind of segment to the test about identifying and naming a type of a chemical reaction. This is not like what you see in the books. It is not like what you see on the practice tests. Those are much more advanced than this. When I actually take the test, I see these. There are only a few possibilities, and this is the only thing they'll ask you. So anytime we have a chemical equation of any kind, we have reactants on the left, products on the right. The arrow is a chemical reaction happening. And they may give you a chemical reaction, and they're always going to look ugly. Nobody likes chemistry. Nobody likes chemical equations and what they look like. But my aim with this page of notes is to simply explain what you should look for, because there's just some very simple things that you should just look for when you see those. And automatically, by looking for the right things, you will know exactly what you have in front of you. It's very simple. Synthesis and decomposition are not on the test right now. I put those on there because it really helps simplify things. I strongly recommend practicing and starting this material and understanding this material with A, B, C, and D. Don't use actual chemical equations for a while. And when you do get actual chemical equations, I still label them A, B, C, D. I'll take an obnoxious complex equation and I'll just label it A, B, C, D on the top of it or the bottom of it, wherever I've got some room. And I still do it this way. It's very easy to see it when they're just letters. Synthesis. What does synthesis mean? It means making something. A synthesis reaction would be when two components come together and they make something that is bigger. So in this example, A is an atom, B is an atom, A and B is now a bigger molecule. Decomposition is the opposite of that. To decompose is to break down. So if we had A and B, that was a big molecule. When the reaction occurs and it splits those up, it decomposed the molecule. Like I said, those two have not been seen on the test, but they help you understand what the letters do and they give you some context. The three types that could be on the test, two of which are prevalent, are electron transfer and replacement. Replacement, so I'm going to start with those, and those are at the bottom. Replacement reactions look quite complicated. There are two types. There are single replacement and there are double. There's a very easy way to spot which one it is. A single replacement will have A, B, and C. When you go to label it, there will be three components. I'll show you. This would be A. Ag is a chemical, so that's B. And C. There's not a fourth one. There's not a place I can put the fourth letter. These equations on this sheet, by the way, are actually harder than the real ones. The real ones will look a little cleaner than this. Double replacement has 4. And really, this is not a very good example. I might actually end up giving you guys a different example, probably on the key. And I'm going to write that here. I will put a different example on the key that's a little closer to the test. I actually was editing these notes from something else that I've used them for. And I didn't actually get around to changing those. I was going to change them to look like the test. So don't worry about those. Understand single and double replacement from a standpoint of A, B, and C, and then A, B, C, and D. On the two most recent mocks, 5 and 6 science mock, I did these and I explained them in the same manner. So you do actually have some practice upcoming that is accurate to the test because I wrote it into the mocks. I just forgot to edit the test or to edit these notes. A, B, and C, the way that they will behave, there's a couple of possible ways. So a single replacement either looks basically like this, or it looks like this. So what you're seeing here is when you go to label them with your A, B, and C, there's only 3 places you can label. Initially, on the reactant side, and to understand chemical reactions and identify them, it's very important that you really keep things in your head as reactant side, and that's the left side, that's before the arrow, before the reaction, and then the product side, which is after the reaction, which is after the arrow. On the reactant side, 2 of the 3 letters will be paired. They'll be together. 1 of them will be by itself. When you get to the other side of the arrow, it will have somehow swapped, which also translates to 1 of the letters moved. So if I had AB and then C, then now I got A and BC. So B moved. Basically, B moved from here to here. That's 1 replacement. That's 1 thing moving from one spot to another. In a double replacement, needless to say, 2 things move. So there's 4 of them to begin with, which gives you a dead giveaway. Really, you can answer them just by knowing if there's 3 or 4 components, because you can't have double replacement if there's not 4 components. Double replacement is like A, B, C, D, and 2 of the letters move. So both pairs will switch. So like AC and BD. There's like 3 or 4 ways it can happen with the sequences of the letters. It doesn't matter how, but 1 of the parts of the pair will move from each side. They'll swap spots. And there are 2 replacements between one side and the other. So that is single and double replacement. I strongly recommend playing with those with ABC and ABCD. Once you really get the hang of that and you can see it, and you get the hang of labeling those and you see them on the mocks, it won't matter to you what the actual equation looks like, because you'll still see it in ABC. So that's the best way to learn it, is like a computer programmer learns code and they see everything in code, even if the code is wrong. So that's what I would do with those. Electron transfer has to do with what we just talked about, and that makes it simple to learn now. Oxidation and reduction. We heard those words when we talked about cell respiration. Cell respiration makes energy using oxidation and reduction. And if you remember, the way I described oxidation and reduction was as basically like a movement of electrons that causes energy to be made. So when you move negative charges back and forth, or you move them down an electrical gradient, you create energy, basically. Electron transfer reactions are reactions like we just did with sodium and chlorine, where a charge changes. The charge changes because an electron is either lost from the molecule in question or gained to the molecule in question. You will know immediately, as soon as you glance at this, you will know whether you have an oxidation reduction or a replacement. Why will you know that? Because replacement will not have pluses or minuses in it. So whatever the equation is, whatever wacky chemical equation they give you and ask you about, if it's replacement, you will not see pluses and minuses. You'll see molecules and you'll see them move. You will not see charges at all. So if there's no charge in the question example, there's no charge on our A, B, and C, you don't see any pluses or minuses in any of that, it has to be one of the replacement reactions. It can't be oxidation reduction. If you look at my example here, I still used A, B, and C. And I put 2 plus, 2 minus, 4 plus, 4 minus. I put numbers and charges. You understand what those are from the discussion we just had. If I gain 4 electrons, I'm going to go from neutral to -4 in charge, because I'm going to have 4 more electrons than I do protons. If I give away electrons, I am giving away negative quantities, which is going to cause me to actually end up with more protons and less electrons, and I'm going to move in a more positive direction. bottom line, oxidation is when electrons are lost. So that's sodium in our previous example. Sodium chose to give its electron to chlorine. So it lost that electron. Sodium became more positive or became positive, depending on where it was when it started, because it's got less negativity. And of course, remember, the positive charge never changes. So you either get more negativity, which lowers your charge, or you get less negativity, which will cause it to go into the positive. Don't worry about the numerical part, because where you start determines where you finish. So it's not true that losing an electron causes you to go from 0 to plus. And it's not true that gaining an electron, which is called reduction, causes you to have a minus. What's true is the number increases if we're oxidized. So if we get rid of an electron, whatever oxidation number we have here will get bigger. So if I had 2 plus, that's already positive because it was in another reaction before this reaction, but I'm even more positive now. I got bigger, I got even more positive, and what that results in, what that results from, I guess is what I mean, is I have a certain number of protons. And when I give away an electron, the difference between my protons and electrons leans further to the side of the protons. So I have more protons than electrons to begin with here. I have 2 more protons than whatever electrons I have. And then I lose another electron, and now I have 3 more protons than electrons. So the way you recognize that an oxidation reaction happened is a molecule on one side has a smaller charge. And when I say smaller and bigger, I mean like the number line. So any negative number, the bigger the number with a negative sign in front of it, the smaller it is. So you can kind of look at a number line, kind of think like this, -1, 0, 1, 2, 3. So if I'm here, I get more positive even if I just go right here and I'm still at negative. That's still more positive than I was. Reduction is where we gain an electron. They kind of sound backwards, and there's a reason that they're named that way, but the way I always remember which one is which, reduction is a gain of electrons. That sounds backwards, which makes it memorable. The reason they do that is the overall charge is reduced. When you gain electrons, your number goes down. That's a reduction in your number. That's why they call it that. Whichever one makes sense to you. I always think about the word gain and the word reduce are opposites. That makes me remember it. And then if I know that reduction is gain, then I automatically can also know that oxidation is loss. And so here you'll see I was at 2 minus, so I was already negative, but I'm further negative here. So I gained 2 electrons. And the way that that might be said is that C, and they'll name it, you'll be talking about a certain molecule so that it's not confusing. You'll say that C was reduced by 2 or something to that effect. This is all logical. Don't worry about the way they say this because it's very logical and you don't need to memorize anything about it. You'll be looking at a certain molecule and they'll name it. You'll know who you're focused on. And you'll say, you'll determine on your own before you go to look at the answers, is this oxidation or is it reduction? Or if there's no pluses and minuses, it must be a replacement. Then you'll think about whether it was reduced by 2 or reduced by 1. Make sure you've decided between oxidation or reduction first. There may be a simpler question that actually just says, what kind of reaction is this? And you say, oh, it's an oxidation/reduction. That would be an easier question. That would just be a question that says, when you see that there's charges that are being changed from one side to the other, you understand it's oxidation and reduction happening. Go back through that explanation if you need anything to be clarified or slowed down or anything. That was a fast explanation. Go back through that if you need to, ask questions if you need to. It is explained again on definitely Mach 6 and I think Mach 5, but definitely on Mach 6 it was explained. We talk a lot about diffusion, and I'm not gonna talk more about diffusion. Diffusion is how most things in the body happen. Diffusion is a natural movement of something to a place that makes more sense for it to be versus the place where it is. And when we say diffusion, we're talking about a natural movement. So there are cases when things need to move in a way that's not as natural, like active transport. That would be where you actually have to put in energy. So that's like pushing somebody that's on a sled up a hill would be active. You got to put in energy and muscle to actually push them up a hill, where if you just drop them down a hill, that's totally passive transport. That's like diffusion. So make sure, just a review, this is all review for you guys. A solvent is a liquid that you dissolve something into. The solute is the thing that gets dissolved into it, and then it has some sort of concentration. We talk about this in humans. So we're talking about our cells and then the stuff that is around our cells, the stuff that is outside of our cells. So when we talk about these solution types, there's hypertonic, isotonic, and hypotonic. Isotonic would be where the balance of water is the same in your cells as it is around your cells, and H2O is moving back and forth because that's what H2O does, but we're not trying to change something in balance. Isotonic is the goal. That's what we use IV fluids for, is to get someone isotonic. If someone is hypotonic, these are our cells. Remember that, or you'll get confused on which one is which. Hypotonic means that there is the solution our cells are sitting in has less solutes than our cells do. In other words, in a hypotonic solution, remember these are the solutions that our cells are sitting in, the water comes into our cells because our cells have more solutes in them. Water follows solutes. Water follows sodium. Wherever sodium goes, water goes. You will learn extensively in pharmacology about diuretics. And that's exactly what diuretics do. The way that we get people to lose water is we get them to lose sodium. The way we get people to gain water is we get them to gain sodium. When you give an IV fluid bag, you're not just giving them water, because that wouldn't do anything. You're giving them salt water, because water follows sodium. So when you want to take water somewhere in the body, you put sodium there. This would not be a good situation. So this would be someone who somehow got into a situation where their electrolyte levels in their body fluids were really bad. So this is someone who has no sodium in their surrounding tissues. That's going to cause the water that is in their body to go into their cells because there's more tonic in their cells. That could eventually cause the cells to rupture. There's a picture of one of them rupturing there. Hypertonic, again, hypertonic solution, meaning the things that are outside of your cell have more solutes, more sodium, and the water leaves your cells to go see that sodium that is outside of your cells. This will cause the cells to shrivel and shrink, which is also bad. So hypo and hypertonic are both bad. You might see them mention those words in the context of a certain type of channel, and that's going to be this last page of biology. So water molecules always move in and out of cells. Cells have a semi-permeable membrane. We've talked about that. Simple diffusion is how a lot of physiological things happen that we've talked about. It's very slow, but water can go in and out of cells all the time. There are hydrophobic regions that don't like water through here. And so it's a slow process because basically the water has to kind of sneak through there. There are a lot of cases in our body where that's not good enough because it's too slow. And we might use a carrier, or we might use a certain type of channel to get water into the cell faster or out of the cell faster to regulate something. Different types of molecules, so we're not just talking about water, although we're going to largely stay focused on water, can move through the membrane in different ways at different speeds in different situations. Lipid solubles, so the opposite of water is fat. They do not get along at all. They can just go right through the cell membrane. So hydrophobic is water phobic. There's no lipid phobic anything, and most of the membrane is made of lipids. So if you are a fat molecule or a fat-driven molecule, you will go right on through that membrane. That's what this first thing shows. Lipid insoluble solutes. So this is like sugar, amino acids, things like that. They actually have to use carrier-mediated, don't memorize this, facilitated diffusion. Facilitated diffusion is where it is diffusion because, so the difference between diffusion and active transport is going somewhere that does not make sense. It's going against the grain. That's like pushing a sled up a hill. Why would you push a sled up a hill? The point of a sled is to go down the hill, right? And then it causes energy input because that's not natural. That's not how you're supposed to use the sled. Diffusion is where we're going in a logical place. Now let's transfer sledding to sodium and water. It is natural for water to move toward sodium. That is natural. That will always happen. So we call it diffusion because that's a natural process. To move water away from sodium does not make any sense. Not to say there's not lots of valuable places where we do this in our body, or we wouldn't even have active transport, but it makes no sense physiologically. So it can't happen naturally. It has to be like active transport. A molecule has to come and grab a hold of this thing and use energy to force this thing where we're trying to put it because it doesn't make sense for it to go there. So a couple of examples of that: going uphill in a sled, shoving your way into a room that is densely packed with people already. That is not natural. That will require energy input if you're going to try to get across a room that is just wall-to-wall people. It would make a lot of sense to get out of that room. It would not make sense to go in it. So that's the difference in diffusion and active. I do not see questions on the TEAS about active transport. What I see is lots of simple diffusion, which is just all the natural ways that our body works and natural water through the membrane. And I see facilitated diffusion very occasionally. Again, I don't see this as an answer on the TEAS. I'm just letting you know what it is, I guess. Facilitated diffusion is where this guy, this is a channel protein receptor type thing. Obviously, this is a mechanism that is designed to let a certain type of molecule in and then put it into the cell. This is molecules we don't care about, so we don't care about this process right now, but that's another way that it happens. Channel-mediated facilitated diffusion, kind of the same thing. So both of those are kind of things we don't really test over, but you kind of need to understand so you understand what the wrong answers are and why they're wrong. Osmosis is defined in a very weird way on the TEAS. The TEAS defines osmosis, in my personal opinion, incorrectly. And that's something that really took me quite some blood, sweat, and tears to figure out. I could not figure out why I was missing their question on this because I know a lot about this. And basically what I ended up finding out, the way that the TEAS looks at osmosis is when the body wants to move water quickly into or out of a cell, it uses a channel called an aquaporin. You're seeing that right here, and I also have it blown up on another page. This is a channel that just opens up. You can see it's just a big open tunnel to just let water pour in or pour out much more quickly than how it would go through the membrane. The TEAS considers that osmosis. I'm shocked by that. I'm still shocked by that. I don't consider that osmosis. Osmosis has more to do with a numerical chemical balance than it does this. But I was able to absolutely, without a doubt, determine that this is what they consider it. And since I'm totally out of time, I'm just going to tell you what this is. There's a series of questions that basically says, in a hypertonic solution, aquaporins are used to move water. And this is what process. So you've got some type of solution. It could be any of the three, really. It doesn't matter. And they say it's aquaporins that are going to move the water. And they want to know whether that's active transport, facilitated diffusion, diffusion, or osmosis. Well, if it's aquaporin and you're on the TEAS, it's osmosis. That is an osmotic process. Not exactly correct scientifically speaking. If you're taking another entrance exam after the TEAS, you will have to reroute your thoughts a bit on that. So I will record the general science segment of this as soon as I can. I have an appointment to go to, and as soon as I get back, I will record the general science segment. And that is it for this segment. So there are 3 parts to this video. Again, review anything you need to before you go on to the next one, especially now that we're on to the general science, and I will see you guys there.